We are told that computers understand only two things, 0 and 1, yes and no, on and off. This binary foundation is often presented as a fundamental law of nature, as unchangeable as gravity or the speed of light. But what if I told you that this was never a scientific necessity, but rather a historical accident? What if the very architecture of our civilization is built upon a convenient lie, a trap that has limited our potential while we weren't looking? Welcome to a journey into the shadows of the digital age, where we uncover a path that was abandoned not because it was inferior, but because it was too late. This is the story of the third path, a forgotten logic that could have redefined intelligence itself. Before we dive into this hidden history, I invite you to join our community. Please subscribe to the channel and turn on notifications so you never miss an exploration into the ideas that shape our reality. By the end of this story, you may never look at your smartphone or your laptop the same way again. To understand the trap, we must go back to the dawn of the computing era in the middle of the 20th century. In those days, engineers were not trying to build the most efficient machines possible. They were simply trying to build machines that worked at all. The early pioneers like Claude Shannon and John von Neumann were wrestling with the immense physical fragility of vacuum tubes and mechanical relays. These components were notoriously unreliable, prone to overheating, and sensitive to the slightest fluctuations in electrical current. In such an environment, complexity was the enemy of progress. Binary logic emerged as the ultimate engineering compromise because it offered the widest possible margin for error. If you only have to distinguish between a high voltage and a low voltage, or a pulse and a silence, you can afford a lot of noise in the system. Even if the signal is degraded, a machine can still tell the difference between something and nothing. This reliability was the bedrock upon which the first digital empires were built. We chose binary because it was the safest bet for a world that was still learning how to harness the electron. However, safety and pragmatism are rarely the same thing as optimization. By standardizing on base 2, we effectively traded information density for simplicity. In mathematics, there is a concept known as the radix economy, which measures the efficiency of a number system. Theoretically, the most efficient base for a computer is not 2, but the mathematical constant e, which is approximately 2.718. Since we cannot easily build hardware based on a transcendental number, the closest integer is 3. By choosing 2 over 3, we accepted a hidden tax on every calculation performed by every machine in history. Binary imposes a ceiling on how much information a single switch can hold, forcing us to use more switches, more wires, and more power to achieve the same result. We have spent billions of dollars and decades of research shrinking binary transistors to the size of atoms. But in doing so, we have merely been perfecting a suboptimal design. We are building faster horses when we could have been designing engines. Today, this legacy has created what we might call the skyscraper of inertia. The modern computing stack is a gargantuan structure of interdependent layers, from the physical silicon at the bottom to the user interface at the top. Every line of code written in the last 70 years, every compiler, and every operating system assumes a binary world. To change the base of our logic now would be like trying to replace the foundation of a 100-story building while the people inside are still going about their daily lives. The problem is no longer one of mathematics or physics, it is one of economics and education. We have trained generations of engineers to think in bits, and our entire global supply chain is optimized for the production of binary chips. The cost of switching is so high that it feels impossible, even if the alternative is demonstrably better. This is the definition of a technology trap, a system that is so successful it prevents its own evolution. Yet, history shows us that a different path was once taken, and it actually worked. In the late 1950s, while the United States was doubling down on binary systems, a team of researchers at Moscow State University was building something radical. Led by Nikolay Brusintsov, they created the Setun computer, a machine that operated on balanced ternary logic. Instead of just 0 and 1, the Setun used 3 states, -1, 0, and +1. This was not a theoretical exercise, it was a fully functional, high-performance machine that proved the power of base 3. The advantages of the Setun were immediately apparent to those who understood its architecture. Because it used balanced ternary, the machine could perform arithmetic with incredible elegance. For example, negative numbers were handled naturally without the need for a separate sign bit, which simplified the circuitry significantly. The Setun required fewer components to perform the same tasks as its binary contemporaries, which led to lower power consumption and higher reliability. It was a masterpiece of minimalist engineering. Despite its technical brilliance, the Setun computer became a casualty of the very ecosystem trap we see today. The Soviet industrial machine was not set up to mass-produce such a unique architecture, and there was a lack of compatible software and tooling. While the Western world was rapidly standardizing on binary, the Setun remained an isolated island of innovation. It eventually succumbed to political pressure and the sheer momentum of the binary status quo. Superiority, it turns out, is no match for market dominance and compatibility. To understand why ternary is so compelling, we have to look at how it would work at the level of the transistor. In a binary system, a transistor acts like a simple light switch, either on or off. In a ternary system, that same transistor or a small group of them could manage 3 distinct voltage levels. This would allow a single unit of information, called a trit, to carry significantly more data than a bit. This increased density means we could shrink the physical footprint of our processors while simultaneously increasing their power. Think of it like a highway system where we have added a third lane without increasing the width of the road. By using 3 states, we reduce the amount of switching and wiring required to move data across a chip. Every time a transistor switches states, it consumes energy and generates heat. If we can achieve the same computational result with fewer switches, we drastically reduce the thermal and electrical costs of computing. This isn't just a marginal gain, it's a fundamental shift in efficiency. However, moving from theory to reality brings us to the core obstacle that has kept ternary in the lab for decades. Binary is robust because the gap between 0 and 1 is massive, creating a dead zone that protects the signal from noise. In a ternary system, we have to pack 3 states into that same voltage range, making the margins much narrower. This makes the system incredibly sensitive to electrical noise, thermal drift, and the tiny variations that occur during manufacturing. One small spike in heat could turn a 0 into a 1, or a -1 into a 0. This physical reality check is why binary has remained king for so long. It is easier to build a billion cheap, imprecise switches that only need to recognize 2 states than it is to build a billion precise ones that can handle 3. But we are now entering the end of the era of easy scaling. For decades, we followed Moore's law, doubling the number of transistors on a chip every 2 years by making them smaller. We have reached a point where transistors are so tiny that they are literally bumping into the limits of physics. In this post-Moore's law world, we can no longer rely on simple miniaturization to give us more power. We have to get smarter about how we use the space we have. This is why the conversation around ternary logic is returning with such force. The challenge today is not just about raw speed, but about intelligence and efficiency per watt. If we cannot make the switches smaller, we must make the switches do more work. Modern transistor designs, like those using gate-all-around technology, are finally making it possible to control multiple states with the necessary precision. But we must distinguish between a successful laboratory demonstration and mass production viability. A researcher can spend months calibrating a single ternary chip to work perfectly in a controlled environment. A factory in Taiwan, however, needs to produce millions of these chips every day with near-perfect yield. Factors like aging, where the materials in a chip degrade over time and change their electrical properties, become massive hurdles for multi-state logic. We need systems that are not just efficient, but resilient over years of heavy use. This brings us to the first real-world battlefield for ternary logic, the massive data centers that power our digital lives. These hyperscale facilities, owned by companies like Google, Amazon, and Microsoft, are facing an unprecedented energy crisis. As artificial intelligence models grow larger, the power required to train and run them is skyrocketing. In this environment, even a 5 or 10% increase in efficiency is worth billions of dollars. This is where the surgical application of ternary logic could first take hold. Rather than replacing every computer in the world, we are likely to see ternary logic used as a specialized accelerator. Imagine a standard binary processor that offloads specific, complex mathematical tasks to a dedicated ternary block inside the chip. This hybrid approach solves the adoption dilemma by maintaining compatibility with existing software while providing a turbocharger for the most demanding workloads. It is a path of evolution, not revolution, allowing us to slowly integrate the third path without tearing down the entire skyscraper of inertia. For this to work, we must pass the reliability gauntlet. Any new system must have built-in self-calibration and fault isolation. The chip of the future will need to monitor its own health, adjusting its voltage thresholds in real time to compensate for heat and wear. Reliability, not just mathematical elegance, will be the ultimate deciding factor. We are no longer in the era of the Setun, where a few dozen machines were enough to prove a point. We are in an era where billions of lives depend on the absolute stability of our digital infrastructure. Looking beyond silicon, the materials question becomes the next great frontier. Current semiconductors are forced to behave in a binary way, but new materials like graphene and carbon nanotubes often have natural multi-state properties. These materials allow for cleaner energy spacing between states and significantly reduced noise. If we can master the supply chain for these next-generation materials, ternary logic won't just be an option, it will be the natural way to build computers. We would be moving from a forced binary logic to a logic that flows with the grain of the universe. Ultimately, the driver of this change will be economics, not ideology. We are reaching a point where the cost of energy is the primary bottleneck for technological progress. If AI is to become as ubiquitous as electricity, it cannot continue to consume energy at its current rate. Ternary logic offers a way to break the link between performance and power consumption. Efficiency is becoming the new competitive leverage, and the companies that can master multi-state logic will have a profound advantage in the marketplace. We are already seeing pressure from the giants of the industry. Cloud providers are no longer satisfied with off-the-shelf chips. They are increasingly designing their own silicon to meet their specific needs. This co-design between those who write the software and those who build the hardware is the perfect environment for ternary logic to re-emerge. When you control the entire stack, you have the power to change the rules of the game. The binary-only rule is starting to look more like a suggestion than a law. This marks a profound paradigm shift in how we think about progress. For half a century, the goal was brute force scaling. More transistors, more clock speed, more heat. But the new race is about efficiency over size. We are learning that the most powerful way to advance is not always to add more, but to do more with what we already have. Ternary logic is the ultimate expression of this philosophy, a way to unlock latent potential that has been hidden in plain sight for decades. This lesson extends far beyond the realm of hardware and silicon. It is a principle that we can apply to our own lives and our own work. We often fall into the convenience trap, choosing the simplest or most obvious path because it is what we have always done. We view our choices in binary terms, success or failure, right or wrong, yes or no. But true intelligence and true efficiency often lie in the third path, the nuanced space between the extremes. Just as a trit holds more information than a bit, a nuanced perspective holds more truth than a binary one. As we look toward the future, we should see ternary logic not as a replacement for binary, but as a partner. The future of computing is likely to be a diverse ecosystem of different logics and different materials, each chosen for the specific task at hand. We are moving away from the one-size-fits-all approach and toward a more sophisticated, layered understanding of information. The binary age was a necessary chapter in our history, but it is not the whole story. It was the foundation, but it is not the ceiling. As we close this exploration, I want to leave you with a question that goes beyond technology. Where in your own life are you stuck in a binary trap? Are there decisions you are making or beliefs you are holding simply because they are the most convenient or the most familiar? What would happen if you looked for the third path, the one that is slightly more complex but infinitely more rewarding? Sometimes, the most important breakthroughs happen when we stop asking, how can I do this faster, and start asking, is there a better way to do this at all? Thank you for spending this time with me today. I wish you health, clarity, and the courage to look beyond the binary. Don't forget to subscribe to the channel to join us for our next deep dive into the hidden forces of our world. Until next time.